Hello, this is Graham Neubig, and welcome back to CS 11747, Neural Networks for NLP. This time I'll be talking about models with latent random variables. So we've talked before about discriminative versus generative models, but just to recap, discriminative models calculate the probability of an output y given an input x, whereas a generative model calculates the probability of a variable px, or maybe the joint probability of multiple variables p of x and y. So if we think about which of the following models are discriminative versus generative, what about a standard bi-LSTM POS tagger? In this case, this is a discriminative model because we're taking an x and then we're calculating the probability of part-of-speech tags y directly. What about a globally normalized CRF-based part-of-speech tagger? This is actually still a discriminative model because it's calculating the global probability of the sequence y, but it is still globally calculating the conditional probability. A language model, on the other hand, is calculating the probability of an input sentence, so this would be classified as a generative model. And if we think about types of variables, there's a few different ways that we can break them down. So observed variables versus latent variables. Observed variables are something that we can see from our data. For example, the x, the text x, which we get just from text that we observe anywhere, or even the labels y, which are provided by annotators, they're still nonetheless provided to us at training time. A latent variable, on the other hand, is a variable that we assume exists, but we aren't given the value. And we have deterministic versus random variables. So deterministic variables are calculated directly according to some deterministic function. So there's no probability distribution over these variables given whatever they are calculated from. It's just we're guaranteed to get the same one every time. Random or stochastic variables, on the other hand, obey a probability distribution and may take any of several or even infinite values. Okay, so now let's do a little quiz about what types of variables particular variables are. So if we have an attentional sequence model using maximum likelihood estimation and teacher forcing, are the following variables observed or latent, and are they deterministic or random? So what about the input word IDs f? The input word IDs f are observed, but we could consider them random variables because we assume they were generated according to some process where people speak or something like this. So we assume that the input to our model is some sort of, is generated according to some process that generates our data. So these would be observed variables, but random variables. Now, what about the encoder hidden states? The encoder hidden states are deterministic variables because they are calculated directly from the word IDs with no sort of random sampling or anything like this. But at the same time, they're latent variables because we don't have any observed data that tells us what these are. The attention values A. Now this is a little bit tricky. The attention values, we normalize them to make them look essentially like a probability distribution using the softmax function. However, these variables are deterministic variables because we never do any sort of sampling from them or anything like this. So these are latent variables, but they're deterministic, like the encoder hidden states. The output word IDs E, so these are also observed variables because we can observe them in our training data, but at the same time they're random variables, and we assume they were generated according to some data generating process, maybe by humans doing translation, and they can also be sampled from our model. Okay, so now let's think about latent variable models. So a latent variable model is a probability distribution over two sets of variables, x and z, where the x variables are observed at learning time in a data set, and z are latent variables. But in contrast to the hidden states or attention matrices that we talked about before, these z variables are not deterministic, but rather they're random variables. So what types of latent random variables are we able to use in training models? So some examples of this here are latent continuous vectors. So basically we have a latent vector, kind of like a hidden state in a neural network, that instead of being a deterministic variable is a random variable, and we can calculate probability distributions over it, etc. We can also have latent discrete vectors. The most obvious example of this, or the most common example of this, is a topic model that induces topics over text. And they can also be latent structured variables, like hidden Markov models or tree structured models. So I'll talk about each of these in turn, basically, as we go forward. So the most fundamental idea here is variational autoencoders. And variational autoencoders follow this latent variable model here. And basically, we have an observed output x, which we assume to be, let's say, a continuous vector for now. And then we have a latent variable z that is generated from a Gaussian, normal standard Gaussian here. And then we have a function f parameterized by theta that maps from z to x, where this function is usually a neural network. So if you remember from the previous class on adversarial learning, this functional form looks very similar. In fact, it's exactly the same between these models. So both generative adversarial networks and this kind of standard variational autoencoder both are using the same underlying probabilistic model. However, the way they are trained is different, and I'll talk about that in a second. So here's an example of something like this. So let's say we have a somewhat complicated distribution. In this case, it's not actually that complicated. It's just a circle, things distributed according to a probability distribution on a circle. But the way the underlying model would work is we would generate points according to a Gaussian, and then map each of those Gaussian points using a neural network onto one of the points over here. And a variational autoencoder basically allows us to sample according to this very simple Gaussian distribution, but then make this output be any arbitrarily complicated distribution. So basically, for each data point I, we draw latent variables according to a prior probability over the latent variables, and then we draw a data point. And so then the joint probability distribution over the data and the latent variables is the product of these two probabilities, the prior and the likelihood of the data. So in order to train this using a neural network, we need to have a loss function. And we would like to maximize our corpus log likelihood. And the way this works is we sum over the corpus and have the log likelihood of each data point in the corpus, like we do normally. And for a single example, the marginal likelihood is the integral over all of the latent variables. So basically, we don't know what the latent variable actually is. So we would like to take the integral over all possible assignments of this latent variable. Unfortunately, however, this is not tractable because unless we put very strong constraints on the functions that we're allowed to use here for the prior and the likelihood function here. And we don't really want to do that because that would limit the expressivity of, for example, the neural network that we could use here. So what we do instead is we approximate this integral by sampling and then summing over all of the samples. And so here we take the sum over samples, where the samples are derived according to the prior distribution here. So one issue with this sampling, however, is if we go back to our previous example here, let's say this point corresponds to this point over here. However, if we just randomly sample according to the Gaussian distribution, it would be the case that we would be very unlikely to get this point, or essentially infinitely unlikely to get this point. So what would happen here is these samples would essentially give us no like probability whatsoever, or a very low probability. So what we'd like to do is we'd like to do a more intelligent way of sampling latent variables that allows us to raise the probability that the latent variables we look at actually give us a high conditional probability of the output. So the way we do this is through something called variational inference. So we have two tasks of interest. The first interest is to learn the parameters of this probability distribution here, theta. And another thing that we'd like to do is we'd like to do inference over z with the posterior distribution here, which means that given the parameters theta, we'd like to calculate the probability of z and maybe even the more likely z's. So we could sample from them and make sure that we are able to find sampled latent variables that give us good likelihood. So that is intractable down here. So what variational inference does is it approximates this posterior probability of the latent variables given x by another family of distributions q phi here. And so this itself can also be parameterized by a neural network, for example, which allows us to learn the posterior distribution and do better inference. So what variational inference does is it approximates the true posterior with a family of distributions here. These are also called like the inference network, for example, or the inference distribution. And we try to train the model so that the KL divergence between the inference distribution Q and the true posterior distribution P theta is minimized. And the way we do this is by calculating something called the variational lower bound, also called the ELBO, evidence lower bound. And so the log probability of x is equal to the evidence lower bound plus the scale divergence term here. And the evidence lower bound, more concretely, is the expectation calculated over the inference distribution of the log likelihood given this the latent variable minus the KL divergence between the inference distribution and the prior. And so basically the log likelihood is greater than the ELBO here. So this is a good thing. So basically what we do is instead of minimizing this KL term here, we opt to maximize the evidence lower bound. So another way to look at this is to think of this as two separate terms. One is the reconstruction loss, and one is the KL regularizer here. So the reconstruction loss, basically what this means is we sample latent variables according to this inference network or inference model that calculates a probability of the latent variable. And then we calculate the probability of reconstructing the input given the latent variables. So we have this reconstruction loss that basically tries to train both of them, both of the models in concert to calculate this. And on the right-hand side here, we have the KL regularizer between the inference network and the prior. So what this is doing is essentially it's trying to force the inference network to be closer to calculating something that matches the prior, or in the case of the VAE model that I just talked about, for example, a Gaussian distribution. So we have two basically pressures here. We have one pressure to allow the model to better reconstruct the input, and another model to make the inference network be closer to the prior. And so this is what it looks like. We have the inference network that calculates Z, and then the generator that calculates X. So another way we can think of this is a regularized autoencoder. So we have this probability, or we have this output of Z where that is regularized to try to match the prior. And why would we want to do this? Let's assume that we don't have this KL regularizer now. Now, essentially, we have no constraint on what the space of the latent variables look like. And if we think about a normal autoencoder, the contrast to a normal autoencoder, we have the VAE that basically encourages the latent space to look like in a particular way. Whereas if we have a regular autoencoder with no kind of regularization here, we have no prior and we have no idea what the latent space will look like. So we could be, for example, spreading our output variables all over the latent space. And actually, one thing I'm going to be talking about later is I'm going to be talking about latent variables, for example, textual or structured latent variables, where we actually do have a pretty good idea of what the prior probability over text or other things might look like. And the VAE model gives us a very good method to enforce these priors over the latent variables that we know of. Another reason why we would want this, for example, is the regular autoencoder is not a generative model. So if we just use an autoencoder, we're not able to sample new data from an autoencoder because we have no way of sampling from the Z. And we also can't calculate the log likelihood of data. On the other hand, the VAE, basically we have a very simple sampling process where we sample a latent variable from the prior, and then we sample an output according to this, this generator function here. So how do we learn the VAE? Basically what we do is we can take our input X, we can sample Z, and then given the Z, we can calculate the output. And then we calculate this loss function here where we sample the Z, and then we have the KL regularizer here. So basically both of these are not hard to do. This is actually reasonably simple to calculate if you are assuming that the prior is a Gaussian variable, and you assume, for example, the inference network also predicts a Gaussian distribution over the output given the input. The reconstruction loss we're sampling, so we can calculate the probability of this p theta. However, sampling actually can break our backprop, and this is something we're familiar with from our reinforcement learning class and other classes like this. So if we have this computation graph where basically we take the input, we run it through the encoder queue, and we sample latent variables according to the mean and variance calculated by this encoder queue, then this breaks backprop, and we won't be able to be backpropping the reconstruction loss back into the encoder. So one of the reasons why the VAE is so kind of interesting and widely used is it actually introduces a very simple trick called the reparameterization trick that allows you to backprop all the way back into the encoder without having to do something like sampling and reinforce and other things like that. So as we talked about before, sampling and like reinforcement learning and other things like this are very unstable. They cause training difficulty. So this reparameterization trick is really a key to why VAEs are able to be trained easily. So the way it works is it uses a kind of feature of the normal distribution, of the Gaussian distribution, which is that if we have a mean and a variance of a Gaussian distribution, we can actually sample from a zero mean and unit variance Gaussian distribution, and then multiply the zero mean and unit variance Gaussian distribution by the variance here, and then we can add the mean, and now suddenly we have variables that are distributed according to the distribution that we would like to be generating from. So now you can see the sampling happens before any part of the computation graph, and we can backprop all the way into the encoder, which is a really kind of clever and useful trick. So this is kind of all general, background for VAEs. So here's an example from language, specifically generating sentences from VAE-based models. So remember that using a regular language model, we can use ancestral sampling and generate. We can also generate conditioned on something else, like a conditional language model or sequence model or something like this. But what if we wanted to generate a model with a VAE-based model? So this is generating sentences from a continuous space, a paper by Bowman et al. 2015. And the VAE-based approach is a conditional language model that conditions on a latent variable z. And it's like an encoder-decoder, but the latent representation is a latent variable, and the input and output are identical. So basically we have the sentence x, we run it through the inference network to get a latent variable z, and then we output the sentence x according to the generator network. So all of this can be done with the standard VAE. We use a reparameterization trick like I just talked about, relatively simple stuff. But why would we want to do this in the first place? We already know, for example, that regular language models trained using teacher forcing and maximum likelihood work reasonably well. So what would be the motivation here? One is that they could potentially allow for a consistent latent space that describes sentences. So for example, interpolation between two sentences. And if we have a standard encoder-decoder model, like a standard autoencoder model that we train to do this, if you remember, like what I talked about before, we have no prior over the latent space or over the hidden space in the encoder-decoder model. So what you can see here is basically we auto-encode, I went to the store to buy some groceries, and horses are my favorite animal. And then we gradually step between the two vectors by interpolating the two vectors together. And we can see that halfway through, it starts to generate kind of nonsense, like horses are to buy any groceries or horses are to buy any animal. And the issue here is basically because there are parts of the latent space that really kind of don't correspond to any reasonable semantics at all. And so interpolating between the two does not make a whole lot of sense. If we look at the VAE, however, if we interpolate between the two inputs, we can see that even halfway through the two inputs, we're getting consistent outputs when sampling from the VAE. And this is because, the VAE enforces the prior on the latent space that it is going to look kind of normal, essentially. So this can be, interpolating between two sentences is not, maybe the most interesting, or maybe not the most useful thing to do. We're not going to be doing it very frequently. But let's say we wanted to calculate the semantic similarity between sentences. And if that's the case, then having kind of a consistent space with similar distances between sentences seems like a very good idea. And in fact, we've found in experiments that this can help semantic similarity models as well. Another reason why we might want latent variables is because if VAE can be viewed as a standard model plus regularization, and this might give you some robustness to noise in the latent space, for example. However, there are a few difficulties in training VAE models. Of the two components in the VAE objective, the Kale divergence term is much easier to learn. And the reason why is because to learn the left one, we need to have a good generative model. But to learn the right one, we just need to set the mean and variance of Q to be the same as P. In other words, we set the mean to be 0 and the variance to be the unit vector. And because of this, this can result in the model learning to rely solely on the decoder and ignore the latent variable. So basically, we just completely set the latent variable, the posterior of the latent variable, to be equal to the prior. And this is something called posterior collapse. So this is bad because we would like to have good and useful latent variables. So there's a couple solutions to this. And also one thing I should note is that this is not necessarily ideal from the generative model standpoint as well. It's just kind of a poor local optimum that the model tends to fall in some cases. So solution number one is Kale divergence annealing. And basically what we do is we multiply the Kale term by a constant lambda starting at 0, then gradually increase to 1. And basically this allows the model to learn to use Z before getting penalized. So we gradually phase in this Kale term weight, and then the Kale term can be learned after the generative model has already been learned to some extent. There's also something called free bits or Kale thresholding, where basically we set a fixed maximum to the size of the Kale term. And this can be viewed as basically getting a bit of information, not a bit, sorry, some information about the latent variable for free, which is why it's called free bits. Another solution is to weaken the decoder. So basically what this does is it reduces the capacity of the decoder so that the decoder is not able to form a good generative model of X unless we have information about Z included in there. So one example of this would be if you wanted to change the decoder from a really strong RNN or sequence model to a decoder that uses like more local context, for example. But theoretically, this is still problematic. It can be shown that the optimal strategy is to ignore Z when it's not necessary. Basically, we can do things like using word dropout to occasionally skip inputting the previous word in X, or use a convolutional decoder limit context, etc. Another solution, the final one I'm going to talk about is aggressive inference network learning. So basically, the idea here is that the inference network, Q, actually falls behind the actual posterior. So if we just train the inference network better, then the inference network can be trained separately, and then the generator network learns to use the latent variables better because the inference network is more effective at learning, producing them at the very beginning of training, preventing falling into local optima. So basically the idea here is that you train these separately with the inference network being trained more aggressively or for more steps. Okay, so finally, I'd like to talk about handling discrete latent variables, because up until now we were mainly talking about continuous latent variables. And so with respect to discrete latent variables, many variables are better treated as discrete, like the part of speech of a word, the class of a question, writer traits like left-handed or right-handed if you're looking at handwriting, et cetera, et cetera. And how do we handle these? So one way we can do this, if we have lots and lots of compute and we only have a small number of latent variables, and for discrete variables, remember we talked about the integral being impossible to enumerate over. However, if we only have a few classes, the integral actually becomes a sum, and we might be able to explicitly expand this sum and just calculate, the prior, calculate the likelihood function here, and enumerate over all of them. We could also do sampling. So we could randomly sample a subset of configuration Z and optimize with respect to the subset. There are various flavors, such as minimum risk training, where we want to minimize the risk or the expected loss, maximizing the elbow loss, or also using policy gradient methods like we talked about in the reinforcement learning class. So these are reasonable, but they are high variance, and you need a way to control variance. So it's better to avoid these if you don't need to resort to this. So another trick that can be very useful is reparameterization. And reparameterization is also possible for discrete variables. So if we talked about sampling, we have this categorical sampling method where we basically sample a latent variable according to the categorical distribution. And this, of course, is non-differentiable because we get out a single one-hot vector and cannot propagate gradients back into it. But the way the reparameterized method works is very similar to the way we did the reparameterization trick for a Gaussian distribution. And what we can do is we can take something called the Gumball distribution, which allows us to essentially do categorical sampling where we add in the log probability, add the Gumball noise here, and take the argmax. And so these two methods are basically equivalent. I won't go into the details of this Gumball distribution, but basically trust me on this or look at the papers to read a little bit more. And this is the Gumball distribution here. However, backpropagation still isn't possible due to the argmax, because as we know, argmaxes are not backpropagable. So a way this can be fixed is using something called the Gumball softmax, which allows a way to soften the decision and allow for continuous gradients. So instead of taking the argmax, we take a softmax with a temperature 1 divided by tau. And as tau approaches 0, this will approach the max here. So we have the categorical distribution where we essentially would get a single output, and the Gumball softmax essentially softens this single sampling function here. So this is also another very like nice and clever trick that you can use if we're sampling single random variables. Okay, so finally, I'd like to talk a little bit about application examples of VAEs and NLP. So one example that I already talked about was the continuous random variables for generating sentences from a continuous space. But now here are some examples of discrete random variables. So for example, you can treat a symbol sequence as latent variables. So an encoder-decoder with a sequence of latent symbols halfway through. And so what we have is we have essentially an encoder model. And the encoder model predicts some discrete latent variables. And then we have the decoder model that takes in the discrete like sequence and tries to re-predict the output. So this is basically generating a sequence of latent variables and then decoding. This can be used for summarization, and in the summarization case, basically what they do is they try to, they also add a pointer network, which gives an inductive bias to try to copy from the input. So there's a copy mechanism that allows you to copy from the input, and basically this biases the model to try to make the discrete latent sequence look similar to the input. In addition, they also have a prior over the latent variables. So remember, this is a VAE, so you can add a prior anywhere of any variety you like. And they use a pre-trained language model to try to force the latent sequence to be similar to text that you would expect to see in the wild. So basically, this gives you two nice latent biases that are basically, we would like the input, the latent variable to look similar to the input because you're allowed to copy words. And we would also like the latent sequence to look like natural text. So this can be used for summarization. And basically what it does is it compresses down the input into a latent variable sequence. And there's also something called emergent communication, which is basically attempts to discover language with these symbolic sequential latent variables. So you're given like an image, and then the encoder compresses it into a sequence of latent variables, and then you need to like reconstruct the image or predict which image it was or something like this. So this is kind of interesting in that it's testing the capability of models to learn discrete communication, like what humans do. So if you're interested in that, you can take a look. One kind of important point, if you are interested in human-like language learning, is that humans don't actually, or usually don't actually learn language tabula rasa by just randomly communicating with each other. It's usually an adult teaching a child. But still, you know, this kind of model could be used to model this, this type of learning process. Might be interesting. So another example of things you can do is you can learn tree-structured latent variables. And tree-structured latent variables, basically, we've talked about them before. You are where you calculate essentially the syntactic structure of sentences. So we talked about like tree-structured composition functions and other things like this. And this unsupervised recurrent neural network grammars paper is interesting in that it demonstrates that this can be used to induce a good language model. There are also difficulties here, however, which is that in order to learn a good tree structure, you need your downstream generative model to be able to use this tree structure in an intelligent way. But if your downstream generative model isn't trained well in the first place, then it becomes very easy to have a kind of posterior collapse to very trivial solutions where we have only left branching trees or right branching trees. So this is a very interesting but difficult problem. And this can also be used for, inducing other varieties of tree structure like semantic structures. So this is an example from people in my group, and actually who did this project as part of a class in 11747, where they calculated a structured latent semantic space of semantic parsers and learned it in a semi-supervised manner. So that is all I have for today. In terms of the discussion question, I would like to talk a little bit about what sorts of latent structures, either discrete structures or continuous structure, you might expect to find in a problem. And in particular, maybe latent structure that isn't super easy to annotate in the first place, that you would like to discover kind of tabula rasa from text that you are given. And given this, how could we design a VAE model or other variety of latent variable model to capture this? So that's all I have for today. Thank you very much.